Welcome to Algebra 2. Our first unit is on functions. Some of this will be review from Algebra 1 or from FADA, but some of it will be new material for you. Today we're going to talk about domain, range, and behavior, intercepts, and continuity. By the end of this video, you should be able to identify the domain, range, zeros, and intercepts of a function presented graphically. You should be able to describe restriction and discontinuous domains and ranges, and you will be able to describe the end behavior of a function. So first, let's look at some vocabulary. Our first vocabulary word is domain. That is the set of all x values for a function. It's also known as the input. The range is the set of all y values for a function, or the output. X-intercepts are where the function touches or crosses the x-axis. X-intercepts are also called zeros, roots, or solutions. The y-intercept is where the function crosses the y-axis. In very rare circumstances, will it just touch the y-axis? The end behavior is what happens at the ends of a function. We'll get more into that when we get to the examples. And then there are two ways that we have for writing the domain and range. One is called set notation. That's a way of writing the domain and range that uses set marks, which are the curly brackets. And then we have interval notation, which is a way of writing the domain and range using either parentheses or square brackets, sometimes both. And it describes the intervals for which a function is defined. A continuous function is a function whose graph is a single, unbroken curve. There are no jumps or holes. A discontinuous function is a function that is not continuous. Let's look at a few examples. So we want to find the domain, range, x and y intercepts for these graphs. And we're going to assume that all of the endpoints and intercepts are integers. So for this first problem, we said that the domain was the set of all x values for this function. So the way that I think about these problems is how far to the left does the graph go and how far to the right does the graph go. So if we look at this first example, the farthest to the left that this graph goes is here, which is -4. Then, since this is a continuous function, I can start at this left point and go across the whole graph without ever lifting up my pencil. The farthest to the right this graph goes is 3. So, first we're going to write the domain in interval notation. So we want to say that the graph goes from 4, or -4, to 3. Then we need a couple more rules. So we mentioned that for interval notation, you sometimes use parentheses and you sometimes use brackets. So if you have a closed circle, you're going to use brackets, because a closed circle and the brackets are the same thing as less than or equal to or greater than or equal to. If you have an open circle, you're going to use parentheses, and that is the same as having either less than or greater than. So, since both endpoints have closed circles, we're going to put brackets on both ends of our interval for the domain. To write this in set notation, we said we are going to use the curly brackets. We said that the domain is the set of all x values, so you want to say this curly bracket means the set of x's such that And then we want to say the x's are between -4 and 3. So we'd say -4 is less than or equal to x is less than or equal to 3. And I knew that it was less than or equal to because we had the square brackets here and the closed circles on the original graph. For the range, we want to look and see how low and how high does the graph go. So the lowest that the graph goes is here, which is -3. And we already mentioned that this is a continuous function. I can take my pencil along this graph without ever having to lift it. The highest that the graph goes is 1. So we're going to use similar notation that we did with the domain. The range goes from -3 to 1, and since we have two closed circles, we're going to put square brackets. For the set notation, we have the set of all y values, because the range is the y values, such that the y's are between -3 and 1. And again, I used the less than or equal to symbols because I had the square brackets, because I had closed circles at both ends of the function. Now, for the y-intercepts, this is the point where the graph crosses the y-axis, which is right here. And we're going to write this as an ordered pair. So this is the point 0, -1. And then for the x-intercepts, that's about here. We said we're going to assume that all of the intercepts are integers, so we're going to round that a little bit, and we'll say that it's about to 0. Let's look at another example. For this second problem, again, we want to find the domain. So we want to look at how far to the left the graph goes and how far to the right the graph goes. So on the left, the graph goes to -4 again. And then if I take my pencil along this graph, I can trace the whole graph without lifting up my pencil, so it is continuous. And on the right side, we stop here, which is at 5. So if I'm writing my domain in interval notation, I'd have -4 and 5. On the -4 side of the graph, we have a closed circle, so I'm going to put a square bracket. And on the 5 side, we have an open circle, so I'm going to put a parenthesis on that sign. So you can mix and match the parentheses and the brackets, and that's totally fine. To write this in set notation, since this is the domain, we're going to have the set of all x's such that -4 is less than or equal to x is less than 5. Since there's a square bracket on the -4, we have less than or equal to there, and there's a parenthesis on the 5, so we're going to have just a less than on that side. Then for the range, we're going to look at how low the graph goes. So the lowest point is here, which is not one of the endpoints, and that's okay. And that's at -4. The highest point on the graph is here, which is 2. So our range is going to be from -4 to 2. So at -4, this is not an endpoint, it is part of the middle of the graph. So we are going to use a square bracket whenever you're looking at a point in the middle of the graph, because the graph does equal -4. So we want to make sure that we're using the square bracket to show that the graph is greater than or equal to -4. Same thing on the 2 side. Yes, This open circle is at 2, so that would say it's a parenthesis. But the graph also reaches 2 in the middle of the graph. So it does equal 2 at some point, so I'm going to use a square bracket. So then just like the previous example, we're going to have the set of all y's such that -4 is less than or equal to y, less than or equal to 2. Because I had square brackets on both of those, I have less than or equal to symbols in both places. For the y-intercept, that is that point there, which is 0, 2. And there are multiple x-intercepts in this problem. We have 3 of them. So that's at -2, 0, 1, 0, and 4, 0. Now for this third example. If we're trying to figure out the domain, we want to look at how far to the left the graph goes and how far to the right the graph goes. But there are arrows on both ends. So this means that this graph is going to continue forever, and it's going to continue going out to the left. So if we continue on forever, this graph is going toward -infinity on the left side. Now, this is a continuous function because if I put my pencil on the graph and trace it, I can go along the entire graph without ever picking up my pencil. And then on the right side, it's going to continue going out forever to +infinity. So when I'm writing this in interval notation, infinity is not an actual number, so you can never equal infinity. So we always use parentheses when we have positive or negative infinity. For set notation, a way you might have seen this in Algebra 1 was by writing the words all real numbers. So the way to write that in set notation is the set of all x's such that x is an element of the real numbers. That's another way of writing all real numbers. For the range, we want to look at how high and how low the graph goes. So the lowest that it goes is -4. And then the highest that it goes, since there are arrows, the graph continues going up, so it's going toward +infinity. So to write this in interval notation, we'll say -4 to infinity. Since the -4 is in the middle of the graph does equal -4 at some point, so that's going to be a square bracket. And we already said that infinity is not a real number, so we can never actually equal infinity, so it has a parenthesis. For set notation, another way of describing this is to say that it's any number that is greater than or equal to -4. So we can write this as the set, let me try that again. The set of all y's such that y is greater than or equal to -4. Now the y-intercept is right there, and that's the point 0, -4. And there are 2 x-intercepts, one at -3 and one at +3. So I have -3, 0 and +3, 0. Now for end behavior, we are looking at what happens at the ends of the function. So there is a specific way that we write that, and this part is going to be the same for almost all of the end behavior problems that we do this year. Later in the year, we'll get to a couple situations where it's slightly different. But you want to say, as x approaches negative infinity, f of x approaches blank, and as x approaches positive infinity, f of x approaches blank. So when x is going toward negative infinity, negative numbers are on the left side of the graph, so that is asking what happens on the left side of the graph as we continue going to the left. Is the graph going up forever? Is it going down forever? Is it getting closer to a specific number? So if we follow this graph to the left, it's going down. So we want to say that the function is approaching negative infinity because this is going down. As x approaches positive infinity, positive numbers are on the right, so that's talking about the right side of the function. So as we go to the right, the graph is also going down. So it is getting more negative, so we're going to say that this approaches negative infinity as well. Let's look at the next problem. So the part that I wrote in black is always the same, so I'm going to just start by writing that. As x approaches negative infinity, f of x approaches blank, and as x approaches positive infinity, f of x approaches blank. So on the left side of my graph, as I go to the left, we're going down, so that is approaching negative infinity. On the right side of the graph, we're going up. So we're going to say that we're approaching positive infinity, or just infinity. And one last example. As x approaches negative infinity, f of x approaches blank. As x approaches positive infinity, f of x approaches blank. So on the left side of the function, we're going down, so that's negative infinity. And on the right side of the function, we are also going down, so that is approaching negative infinity. One other thing we can look at with these examples is if you put your pen on these and trace them, you can trace the entire graph without ever lifting up your pencil. So all of these are continuous functions. All right, last few examples. We want to find the domain and range of all three of these strange-looking functions. Now these are called piecewise functions. We'll get more into that later in the year. But finding the domain and range of these is a little bit different. If I look at this first example, the farthest to the left that the graph goes is here, which is -4. Then if I put my pencil here and trace this line, I would have to pick up my pencil to continue on the other part of the graph. So this is a discontinuous function. So I'm going to have to write the domain in two different pieces. So if I follow this piece, it stops there, which is at 1. Then the other piece of the function starts at 2 and continues off to infinity. So when I write this in interval notation, I'm going to say -4 to 1. -4 has a bracket because it has the closed circle. 1 has a parenthesis because it has an open circle. And then I'm going to put this U. This is a union symbol, and it pretty much, in this circumstance, means and. So I am looking at this first interval and this second interval that I'm about to write. So the second part of the function goes from 2 to infinity. 2 has a square bracket because it has the closed circle, and infinity always has a parenthesis. So I'm saying that the domain of this function is the interval -4 to 1 and the interval 2 to infinity. Now, to write this in set notation is a little tricky. I start off with the set of all x's such that, and then I'd write the first part. X is between -4 and 1, and I have the less than or equal to here because I had a closed bracket or square bracket here, just less than because I had the parenthesis on the 1. I'm going to put a comma. X is greater than or equal to 2. Because the second interval from 2 to infinity is the same as x is greater than or equal to 2. Now for the range, we want to look at the lowest point, which is -4. So then here's where it gets tricky. The first piece ends here at 0, but the second piece also starts at 0, and they're both closed circles, which means there is not a gap in the range. Where one section ends, the other section starts. And then this part continues up to infinity. So my range is just going to be -4 to infinity. -4 has an open circle, so I need to put a parenthesis, and infinity always has the parenthesis. Then in set notation, this would be the set of all y's such that y is greater than -4. And I said greater than because there's a parenthesis on -4. It is not equal to -4. Let's look at the next one. If I am writing this domain, I start on the left at -infinity. Then if I put my pencil here and continue along this, I get to this point, and then I would have to pick my pencil up to jump up to this dot, pick my pencil up again to continue along the second part of the function. So this is also a discontinuous function. But on this problem, we start going along this first branch of the function. We get here, we jump up to this point, then we jump to this other branch of the function. So there are no x values that don't have a function value. So this side of the graph is going to continue going over to the right to positive infinity. So my domain for this is going to be -infinity to positive infinity. And as we said earlier, the way we write that in set notation is the set of all x's such that x is an element of the real numbers. For the range, we want to start with the lowest point, which is here at -7. Then this branch of the function continues going up to positive infinity. The other branch starts at 0 and goes to positive infinity. Well, if I say that the range goes from -7 to positive infinity, doesn't that include 0 to positive infinity as well? It does. So I only need to write -7 to infinity as my range. The -7 has an open circle, so I'm going to have a parenthesis, and infinity always has a parenthesis. So in set notation, this is the set of all y's such that y is greater than -7. And I want to point out something to you about x-intercepts on this problem. We have one x-intercept here at -2.50, but we have an open circle here. An open circle means that that point is not a part of the graph. So that point 1, 0 is not an x-intercept. Last example. If we are writing the domain, we want to look at the farthest to the left that the graph goes, which is here at 0. So then if I follow this part, I have to pick up my pencil to continue with the next part. So this is also a discontinuous function. This particular problem is called a step function, which is kind of obvious because it looks like stairs going up the graph. But this first line starts at 0 and goes to 1. The second line goes from 1 to 2, the next from 2 to 3, 3 to 4, 4 to 5. And every time that there's a jump, there is a closed circle. So there are no gaps in the x values of the function. So the domain is going to be from 0 to 5. 0 has a close or a square bracket, and 5 has a parenthesis. In set notation, this is the set of all x's such that 0 is less than or equal to x, which is less than 5. For the range, this is where it gets a little tricky. The lowest that the graph goes is 0, but then there's this gap here. There are no points in that area. The next time that we have the graph is at 1, then there's another gap. Then there's a line at 2, then there's another gap. So when we write the range, if we write it in interval notation, it's a little cumbersome. So the range would be at 0 and at 1, whoops, and at 2, and at 3, and then we need one more, and at 4. So this one is actually easier to write in set notation because the set would be the set of all y's such that y equals 0, 1, 2, 3, 4. Okay? Make sure that you know how to use both interval notation and set notation. You will be expected to know both. You will not be expected to write both on every problem.